We're dealing here with creating a confidence interval when I know the standard deviation of a population. If I know sigma, which is the standard deviation of a population, I'm able to use a z-score because z-scores refer to a perfectly normally distributed curve, and the IQ of a population of 7th grade girls in the whole Midwest is so many people, we know that that's normally distributed. So always for a confidence interval, it's going to be the statistic plus or minus the critical value, CV is critical value, times the standard error of the statistic. Okay, so let's see how that plays out. The first thing I must do is state my three conditions that I have, it's random, normal, and independent. Because the data says that it's a random sample of kids of 7th grade girls, I know that that's random right there. The second thing is that it's normal. Since the sample came from 31 7th grade students, then we know that when I take a lot of samples of a normally distributed distribution, a normally distributed population, and IQ is a normally distributed value across the population, then a sample of 31 of a normally distributed population is going to create a normally distributed distribution. So then I know, because of the central limit theorem, that the distribution of samples means are going to be approximately normal. I have to state that. The third is because a sample of 31, this is actually supposed to be just 31, is less than 10% of the population of all 7th grade girls. So I'm able to take the x mean plus or minus the z critical value times sigma divided by square root of n. And that's going to be, if I took all those values and plugged it into my computer, I would see that this is going to be the x mean. This is the critical value for that size confidence level. 15 is my sigma, and square root of 31 is my n, and that is the final value, and you could figure it out what the two different bounds of the confidence level are. Now, what happens if I only have a sample? I don't know the standard deviation of the population. In this case, I'm looking at the amount of nitrogen oxides emitted by light-duty engines, but I don't know anything about the population, so I can't say I don't have a sigma of the population. That doesn't exist. Instead, I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6. I have about 40, I have 45 vehicles, and I could take data from this sample of 45 vehicles, but I can't say anything else about the actual standard deviation of the population. Instead, I'm going to have to calculate the x mean of the sample, and I'm going to have to also calculate the standard deviation of the sample. That's all I could have. Because of that, I can't say that my distribution is going to be approximately normal. So I can't say anything about the normality of it. I could say it's going to be a bell curve, and therefore I could use the t distribution, but I can't say anything about the entire population. So let's see, what do we do? So let's say I decide that I want to look at a 95% confidence interval. So I know that I have to take a critical value that's going to correspond to this 95%. What we do is we look at this table, which is going to be table B, which is going to be from your, on the AP, you're going to get it. And let's take a zoom in here. If you look over here, we see that this is the t distribution. It actually looks at an upper tail instead of a lower tail like the other one. So what I do is I say, hey, how many cars do I have? In this case, we had 45 cars. So my degree of freedom is going to be 44. Degree of freedom equals n minus 1. In this case, it's 45 minus 1 equals 44. Because it's 44, we're going to round to 40 right here. Okay, we're going to round to 40 because that's what we have. That's all we have. And we're looking at a 95% confidence value. So I take I take this 40, and I take the 95, and I end up with a t critical value of 2.012. So now we're ready to actually do a calculation. We know that for a confidence interval, I need to have my statistic plus or minus my critical value times the standard deviation of the statistic. So in this case, it's going to be my x mean which is the mean level of the chemical that's emitted by these 45 cars, plus or minus my critical value, which we figured out from the previous table, is going to be 2.021, that's my T critical value, times the standard deviation of these 45 cars. Like I take my 45 cars, I put them into my calculator, I do one var stat, and I end up with this S, divided by the square root of my N, okay, which is that value right here, which is going to be 1.329 plus or minus 2.021, sorry, this is a bad plus or minus, times 0.484 divided by the square root of 45, and that actually gives me this T confidence interval. So we're 95% confident that the true mean level of nitrogen oxide emitted by this type of light-duty engine is between these two values. So I'm going to, on the next slide, we're going to go through the 4 different stages to make sure that we do this right. So if we're really doing that problem correctly, we would do our 4 steps. The first thing we would do is that we would say we are looking for, with what percentage confidence, we're looking to see what is the, what is the range that I could expect the true mean of the nitrous oxide emitted by light engine vehicles to be. My second thing I'm going to do is going to plan. I have to state my conditions. I have to say that I have a random sample. I have to say that it's independent because it's going to be less than 10% of the total population of cars. And in terms of normal, I actually can't say that it's normally distributed. I have to say that because of the central limit theorem that it's going to be a bell-shaped curve, but I have to use the t distribution. I'm also going to try to draw my curve. The third thing I'm going to do is do, which is what we did, and figuring out the values. And my fourth thing is going to be to state the conclusion. I can conclude with, I forgot what the values were, with 90% accuracy that the true mean level of chemical that's emitted is between blah and blah. But that's from the previous slide.